In this video, I will show you exactly how to make your own Mandelbrot Zoom. I will give you the code for this using Python, but with the solution I provide, you should be able to easily implement it in other programming languages. Before we begin, I'd like to mention that this is a follow-up to an earlier video I made explaining the mathematics behind how the Mandelbrot set is generated. So if you need a refresher on it, be sure to go check that video out first. Okay, let's get started. Here is my Mandelbrot Zoom code. As you can see, it consists of just two basic blocks. The first being the main function that determines which points are in the Mandelbrot set. And the second consisting of a loop that will take all these points and produce beautiful Mandelbrot images out of them. Now I'll go through it step by step and explain everything that it does. I've also put a link to it in the description section below so you can access it yourself. So the first line here just imports a module called image from the Python library Pillow. This is the only thing we'll need to import, and it will allow us to easily create images and manipulate the pixels however we want. If you don't have it installed already, you can install Pillow by just typing in the command line pip install Pillow. Okay, next up is our main function that determines which points belong in the Mandelbrot set. I named this function Mandelbrot points, and it takes two items in as inputs: the max iteration number that you want to iterate up to, and a complex number c. Now remember, the Mandelbrot set is defined by the equation f of z equals z squared plus c. And there's a useful rule that all the points that belong to the Mandelbrot set have an absolute value less than or equal to 2 at every iteration step. So what this function does is it takes in a complex number c, starts with z equals 0, and then proceeds through the iterative process of applying f of z equals z squared plus c. It then checks at each step if the magnitude of f of z is greater than 2, but it will only do this to a certain number, which we can choose by setting iteration maximum. The true Mandelbrot set consists of only those points that are bounded for an infinite number of iterations. So the higher you set iteration maximum to, the closer it will approximate the true set. And this variable here that I'm calling stability value is what keeps track of whether C is in the Mandelbrot set or not. And if it's not, stability value encodes how quickly it escapes. The initial value I set it to is 1. So you can see that if C is in the Mandelbrot set and we enter this loop, then we'll just go through all the iterations and will never satisfy this if condition. So stability value will remain unchanged, and 1 will represent the point being in the set. However, if C is not in the Mandelbrot set, then at some point this if condition will be satisfied, and we will then change stability value to a new value, I over iteration maximum. So the more quickly C escapes the set, the closer to 0 this value will be, and the longer it takes C to escape, the closer it will be to 1. Okay, next up is the main loop. Each step through this loop will create one image. The three main things that you'd want to change and customize for whatever type of zoom you're wanting to make are these first three lines. In the first line, we'll create a new image using the module we imported at the beginning. I set the mode here to L, which is just a grayscale, black and white type of coloring scheme. You can make it in color by selecting RGB mode, which I've commented out here. The assignment of colors is slightly different for each of these modes, and I'll explain that shortly. The size here determines how many pixels you want the image to be. I just have it set here to 512 by 512, but you can change it to whatever you'd like. The more pixels you have, the higher quality the image will be, but of course it will take longer to create. Okay, so after we create our image, we then want to select the image's center point. This will be a point in the complex plane. So if we select 0 plus 0j, then the image will be centered at the origin. If we select -1 plus 1j, then the center point will shift 1 unit to the left and 1 unit up, and so forth. This will be crucial for creating a zoom because, as you'll see, in order to find interesting structures while zooming in, you need to be selecting the right points to have as your center. Otherwise, you will easily find yourself zooming into regions that are just all black or all white. And that brings me to the next variable, which will be crucial for a zoom. I named this variable desired width. Basically, it's the width of the viewing window that you want. So you'll see if I set it to 4 here with the origin as the center point, then from the center we can go 2 units in either direction and reach the edge. If we set it to 3, then we can go 1.5 units in either direction. And if we set it to 1, then it's only 0.5. And this is how we will zoom in. We simply need to pick a point as the center point, and then just keep making the width of the viewing window smaller. The origin is not good though, because already by just making the width 0.25, you can only see black. A better point is the following. I've also included some other interesting points here in the code that are definitely worth looking at. And you can see that if we just keep cutting the width in half, we continue to see amazing structures throughout. So depending on how you want the zoom to look, you will need to experiment with how quickly you want the width to be changing. This formula should work fairly well, but it also can go quite slow as you get further and further down. So I recommend changing and experimenting with it to get your desired output. Another thing that you'd want to experiment with is changing iteration maximum. As you go further down, you'll see that you need to iterate to higher numbers in order to better reveal structures that are there. Okay, so these next 3 steps just use the variable desired width from above and scales the original image size to the desired width size. And then the last bit of code that I'll explain is how the colors are applied. That's what this loop does. For every pixel in the width direction of the image and every pixel in the height direction, it gets the coordinate of the pixel. It then uses this formula to convert it to a coordinate on the complex plane. Then it calculates what I'm calling the instability value, which is just 1 minus the stability value I mentioned earlier in the Mandelbrot points function. So here it calls that function with a specific iteration maximum value, which of course you can change, and with the complex coordinate of the given pixel. It then assigns a color to that pixel based on its instability value. Here, the range is 0 for black and up to 255 for white. So by multiplying the instability value by 255, this will assign a black pixel to all points that are in the set and a range of grayscale values approaching 255 for points not in the set, depending on how quickly the point escapes. And you'll see here that I also included a block of code that you can use if you want to make a zoom in color. The RGB mode requires 3 inputs to determine the color of each pixel, 1 each for how much red, green, and blue should be assigned. This is just one scheme you can use, but you can also experiment with changing how these are assigned to get different colored effects in your zoom. So this simple code will produce all the images you need. If you want to turn it into a video, then the final step would be to just use FFmpeg or something similar to stitch all the images into a movie.